All right, so I just want to take you through one more problem. This was the one that we didn't finish in class today, and I kind of figured it wouldn't hurt to have another video. So first thing I'm going to do is factor the numerator, and the purpose of that is to figure out, that's a crooked line, is to figure out whether we have a whole or not there. So this factors into x, and remember when you're factoring, you're trying to come up with two things that multiply to this, that if you FOILed everything together or multiplied everything back together, you would end up with this. So two numbers that multiply to -3 are -3 and 1. And I promise you that if you multiply this back together, you get this original. And I notice immediately that I am going to have a whole there. So what I'm about to do is cross off the factors that cancel, because in theory, when you have the same thing in the numerator and the denominator, they can cancel out. But I also know that there's going to be an issue at that factor, that if x happened to be -1, then you would end up having not really like 1/1 or 5/5 or 10/10. If x was -1, you'd have 0/0, which is problematic. And that's what leads to this idea of the concept of a whole, which is something that's problematic, but also sort of removable from your equation. So I know a whole is a location in space, so it needs like an address, it needs a coordinate. And so once I've identified the factor that cancels out, the thing that makes this a 0, which is -1, is going to be the x coordinate. And that's all I get from that factor. Now what I can do is actually cancel the factors out. And this is the equation I'm going to use to answer literally all the rest of these questions, including this part here for the whole. So to figure out the rest of the whole, I'm going to substitute in -1. So -1 minus 3, -1 minus 1 squared would give me -4 over -1 minus 1 is -2. -2 squared is 4, which is -1. So -1 is a whole, and I'm just going to write it like that as an open dot. Okay, so now I'm going to fill in the other pertinent information. So again, remember, you are always going to take information from this source, not from anything else. Never the original, because remember, we modified the original by canceling this factor out. So you're not allowed to look backwards there. If these didn't cancel out, then it would be interchangeable. You could look at any of them. But since they do cancel out, we don't want to look here. Okay, vertical asymptote. So the vertical asymptote is what produces a 0 in the denominator, so x cannot be 1. If x is 1, we have a problem. Sorry, my iPad keeps falling down. So if x is 1, we have a problem, and so we visually represent that problem with a vertical asymptote. End behavior, the degree of the numerator is less than the degree of the denominator, so the asymptote, or the end behavior, is going to trend to 0. And again, I wish it didn't look like that in terms of dashed line, because it gives the illusion that this and this act the same way, and they're very, very different. As I've mentioned, obviously, a bunch of times in class, this is a suggestion, and what happens in the middle is inconsequential. It's really just what happens at the edges that blue line serves the purpose for. Okay, I guess we'll do x-intercepts. That comes from the numerator. So the number that would produce a 0 in the top is obviously 3. So 3, 0 gives us our x-intercept. Note that it will cross because the multiplicity of this is odd. So there's a secret 1 here, which is obviously an odd number. And so we're going to cross through that, whether it looks like this or like this, depends on, my behavior at the asymptote. Okay, the y-intercept. Again, trying to switch my colors so that you guys can see where everything is coming from. So replace x with 0. So if I do that, I get -3/1, which is -3. And that is actually really helpful, because now I know what's happening here. Now I know it's trending down. So many color choices. Okay, so this is trending down. So I'm just going to continue down. Now, this could come through here and kind of tilt back down to this line, but it definitely doesn't, because as we've talked before, remember, use a lot of common sense as you're drawing. if you go up through this, you're going to create another x-intercept, which obviously we only have one. So in theory, this could cross and come back down, but it doesn't because we don't have an extra x-intercept. So I know it's just going to look something like this. From here, I'm going to use my multiplicities, which says that this asymptote, remember the choices as you approach the asymptote are either it's facing down or it's facing up. So it's the same issue on the other side, is on this side of the asymptote here, I could either put an up arrow or a down arrow. There's literally only two options. So how do I distinguish between the two of those? I mean, I could plug in a number that's really close to this, or since I already know what the asymptote behavior is doing here, I can look at the multiplicity of that asymptote. The multiplicity of the asymptote is even. Evens face the same direction. So if it was facing down on this side, it's got to be facing down on the other side as well, so that these match up. And then it makes, I think a lot of sense to go through and back to that intercept. You have nothing else. If I don't connect it, there's a lot of logic that says it only makes sense to connect the stuff that's already there. So I'll connect it. If you remember, the multiplicity of the intercept was odd at odds we cross. So this one does cross. And now it probably goes up for a while, but then it eventually will come down. So does it go up a lot, like a little hill like I've just drawn, or does it just go up a tiny bit and immediately go back down, or does it oscillate a little bit and then trend toward, that's a terrible trend downwards this way? I have no idea, nor do I really care, right? Because these are, if I really zoomed far out of that line, it's sort of like what I would do on Desmos. I'm trying to figure out what is happening at the edges of the graph. I don't so much care about the middle of the graph. What I care about in the middle of the graph is important information, like the asymptote or the intercepts, things like that. But the general structure of whether this waves or comes down quickly is, it's inconsequential at this point. It's not really a pertinent piece of information. Okay, so that's what the picture should look like. Hopefully if we graph in Desmos, which you can always do while you're working alone, or with a team or a group, you can always plot these in Desmos and just see what happens and see if you made an error anywhere along the way. But you should get some important feedback or automatic feedback as you're doing the problem. If, your intercept doesn't quite match up without the algebra, meaning like the picture and the work don't quite sync together, then you probably made an algebraic error somewhere. Or maybe you graphed something. Maybe you missed a multiplicity and it was supposed to cross when it bounced, or vice versa, whatever, right? So you get some automatic feedback in there. Hopefully that was more helpful. I'll try to make some more videos to make sure that you have enough info for the test on Friday. Subscribe to my channel.